So I had mentioned previously that there are three kinds of hazards. There are structural hazards, there are data hazards, the ones that we have seen several examples of in the last few videos, and then there are control hazards. And these hazards are created when you encounter, say, a branch or a jump instruction, and it takes you a few cycles to figure out exactly what place you're jumping to, right? And so by the time you figure that out and by the time you set your program counter to the correct value, a few cycles have elapsed where you've gone ahead and fetched instructions that may really not belong to this program, right? Or instructions that really should not have been executed. And so those instructions have to eventually be squashed, and that leads to a few cycles where nothing useful gets done, and that's equivalent to a stall cycle, right? So now let's look at different strategies to deal with these control hazards. And as I go through this example, I'm going to assume that you have a program that executes, let's say, 100 instructions. And if things go really well, if there are absolutely no hazards, that 100 instruction program should finish in roughly 100 cycles. Now, out of those 100 instructions, 20 of them are branches. And let's say that these are if-then-else statements. So maybe 12 times you go to the then part, and 8 times you go to the else part. And the way this program has been written, the then part comes right after the branch. And if the branch is taken, then you jump to this else location, right? So this is corresponding to the branch being taken, and this is corresponding to the branch being not taken, right? So just recall that the way the program is written, you have the branch sitting over here, and then you have some instructions right after that. And if the branch condition is met, then you jump to another label, and that could be sitting down here, right? So if the branch is taken, then you are jumping here. And if the branch is not taken, then you just continue along the sequential path and execute the instructions that come right after. Okay, so what are the different strategies to deal with this branch, right? So I've just fetched this branch, I have examined what it's doing, what can I do? The first option is to just panic and say that it's a branch. Since I could be jumping somewhere else, let's just not fetch anything in the next cycle. So in the next cycle, you do not bring any instruction in. It's like a bubble flowing through the pipeline. You've just lost a cycle. And then, since it takes 2 cycles to decide which way the branch is going to go in our 5-stage pipeline example, by the end of the second cycle, you've figured out that this branch is either going to the else part or it's executing the then part. Accordingly, you set the program counter and bring in the correct instruction in the third cycle, right? So instruction 1 comes in the first cycle, nothing happens in the second cycle, and the correct instruction is fetched in the third cycle, right? So that basically gives you 1 stall cycle every time you encounter a branch. Since there are 20 branches in these 100 instructions, that adds an additional 20 stall cycles. So the program, instead of taking 100 cycles to finish, finishes in about 120 cycles, right? So that's a pretty steep drop in performance. This is about 20% slower than our design that just didn't have any hazards or any stall cycles at all. Now let's look at option 2, and this is the option that we've kind of been assuming as I introduced this topic. So when we do encounter the branch, we know it's going to take me an additional cycle to figure out which way the branch is going to go. In the meantime, I just do my default operation, which is to increment PC by 4 and just start fetching the next instruction. So I start fetching these instructions from the then part. Okay, and at the end of cycle 2, I figure out, oh, this is actually jumping to the else part. So in cycle 3, I start fetching the correct instruction, and I end up squashing whatever instruction I fetched in the second cycle. If the branch ends up deciding to go along the then part, then things are fine, right? Whatever instruction I fetched in the second cycle just carries on, and that means that there are no wasted cycles, right? So how long does this program now take? So out of these 100 instructions, 20 of them are branches, 12 of them go along the not taken path. And if that's the correct path, then I don't lose any cycles, because from the second cycle itself, I'm fetching the correct set of instructions. Okay, so these 12 cases don't really lead to any penalties. But every time the branch is taken, I've lost a cycle, because one cycle goes by where I fetch instructions from the incorrect fork in the branch. Okay, so the total number of cycles I would now take is 108 cycles, because every taken branch costs me 1 cycle, and a not taken branch ends up being a correct prediction and ends up fetching instructions from the correct place. Okay, so this is what I've been assuming until now. Now let's look at option 3. What this says is, I'm encountering a branch, right? And sometimes this branch goes down to the else part, and the rest of the time it executes the then part. Okay, so what I'm going to do now is I'm going to assume that the instruction after the branch is always fetched and executed completely. I'm never going to squash it. Okay, and this is basically saying that it takes me 2 cycles to figure out which way the branch is going. And there's that one cycle right after I bring in the branch, which is kind of like a limbo state where I really don't know where I'm going. So let's just assume that during that cycle, I bring in something useful and I execute it. And now it's up to the compiler to make sure that something useful gets put into the slot right after the branch. Right? So that instruction after the branch is referred to as the branch delay slot, which says that I execute a branch, but the real fork in the road happens one instruction later. And so the instruction after the branch is almost as if it's going to be executed for sure. And then after that, I either go into the then part or I jump into the else part. Okay, and so if the compiler is smart, it can look at some instruction before the branch and say, hey, this instruction is something that always has to be executed. Instead of executing it up here, let's bring it down here and execute it down here. Right? Regardless of which way the branch goes, I know this is an instruction that will always execute, which is exactly what the programmer intended. Right? Here's an instruction that regardless of which way the branch goes is always going to get executed. I'm just delaying its execution and trying to do something useful while I'm in this limbo state. So if I'm always successful in putting something useful into that branch delay slot, each one of these 20 branches is really not going to cost me a cycle, because the cycle after the branch, while I'm deciding which way to go, always ends up executing some useful instruction, right? So if everything goes well, I can finish this program in 100 cycles, right? So I can get back to that ideal case. In practice, the compiler cannot always find something useful to put here. So in practice, you may end up doing something not very useful, and so you do lose a few cycles. So maybe in practice, this number is closer to, let's say, 103 cycles, right? Still better than this example here. And if everything goes well, you can reach this ideal case. But in practice, it'll typically be a few cycles more than the idealized 100 cycles. So this is with a compiler-based approach. Now this fourth option says, let's not involve the compiler, right? The compiler is basing its decisions on the original source code. It has no idea of what's actually going to happen at runtime. Maybe at runtime, the hardware is smart enough to see what this program has been doing, and it can make a smarter guess. Okay, so you do instruction fetch here. You go through, decode and register read in the second cycle. Normally, we say that this is where you figure out which way the branch is going. That impacts instruction fetch in the third cycle. What I'm trying to do is fetch something useful in the second cycle, right? So what this fourth approach is doing is it's saying that the hardware has some smarts over here that tells me that, based on past history, based on what this branch has been doing in the past, I'm going to make a smart guess about which way this branch is going to go, right? Whether it's going to go execute the then part or the else part. And I make as good a prediction as I can, and I accordingly start fetching instructions from that location in the second cycle. Okay, so if I can build a really good predictor that is correct, say 90% of the time, then for these 20 branches, I'm going to make a correct guess 18 times, and I'm going to make an incorrect guess 2 times. If I do make an incorrect guess, that guess gets corrected by the end of the second cycle, where I do figure out which way I'm going, and I start fetching the correct instructions from cycle 3, and I squash whatever was fetched in cycle 2. Right? So this is similar to this case over here, but this case makes a default prediction that I'm always going to go along the not taken path, and I just fetch the next instruction. Okay, whereas this fourth case says that instead of just blindly fetching the not taken branch, let's make a smart guess. If I can correctly predict branches that are taken, I will bring instructions from the taken side. Right? I'll start bringing instructions along the else part. Okay, so if I make a correct guess 18 times and I make an incorrect guess, say only 2 times, then this program should now finish in 102 cycles, right? Where I'm penalized a cycle only when I make an incorrect prediction. Okay, so I'm going to look at both of these cases in more detail next, but this kind of shows you the 4 different options and the expected performance from each of those 4 options, right? If you just panicked and didn't do anything, it's quite penal in terms of performance, right? And so this is an approach that is clearly not good, and we will not consider it any further. This was the default simple assumption where I just said that by default I'll start fetching instructions from the not taken side. And sometimes that is the correct option. And so I'm only penalized when the branch is taken. That leads to a few stall cycles. And then the third option is to use compiler smarts to do something useful after a branch and just not be penalized. If all things go well, you have 0 stall cycles. But typically, things don't always go perfectly, and you have 103 total cycles. And then the fourth option is to not take help from the compiler, not have a branch delay slot, but have some kind of hardware structure that makes intelligent guesses. And every time you're right, you're not penalized. And so you're only penalized cycles when you make an incorrect guess.